Hi class, in this lecture we'll be discussing the Earth system and defining just what a system is. So I would like to begin with a brainstorm. I'd like you to think about just what a system is, jot down some terms, so pause this video and when you're ready resume. Okay, so maybe you came up with some terms like a system contains numerous parts or many pieces or components that work together and interact to form a whole. And if you came up with something like that, that is excellent. But now I would like to ask you, how do we define this whole? Well, in order to figure out what's inside the system and what is outside the system, we need to delineate a boundary. So in this case, everything inside that boundary is part of the Earth system. Everything outside that boundary is part of the surroundings. So that would be the rest of the universe. All right, the rest of the universe makes up the surroundings. And you can delineate this boundary in different ways. One way we can do it is by using the Kármán line. That is at an altitude of about 100 kilometers or 62 miles. And that is where the atmosphere is too thin to support aeronautical flight. So then let's look at the Earth system more closely. And we can actually break it down into 4 different subsystems or spheres. So the first one we have already talked about a little bit because that's where we placed our boundary layer, right, where the atmosphere became thin. So the first system would be the atmosphere. And the atmosphere is about 130 kilometers thick, just depending on your definitions. And it contains 78% nitrogen, so molecular nitrogen, N2. It contains 21% oxygen, that's molecular oxygen, so O2, 2 oxygen molecule atoms combined. We have 0.9% argon and about 0.04% carbon dioxide. And those are percentages that go along with the dry atmosphere. So, of course, there's something else very important in the atmosphere, and that is water vapor. And so that brings us into our next sphere, the hydrosphere. And the hydrosphere contains all of Earth's water, and this includes both liquid water, solid water, ice, and also the gas, like we were talking about in the atmosphere, the gaseous phase. And on Earth, it is estimated that there's about 366 million trillion gallons of water. So that is a huge number. So we have a lot of water on Earth. And if you took a course in water resources, or if you happen to take environmental science last semester, you'll know that fresh water on Earth is incredibly scarce. And then we have different storage reservoirs within the hydrosphere. So that would include the atmosphere, where we have water vapor stored, oceans, where we have liquid water, we have ponds, rivers, streams, glaciers, where we have solid water or ice, permafrost regions, so that's ice in the ground. So that also brings me to groundwater. And where is groundwater contained? Well, it's contained in our third sphere, and that is the lithosphere. So the lithosphere is made up of Earth's crust and uppermost portion of the mantle. It's on average about 100 kilometers thick, and on it we have plate tectonics that happen, mountain building, volcanic eruptions, and also there's soil. Soil is part of the lithosphere. And one very important component of soil is our earthworms and microorganisms. So that brings me to life. The biosphere is the fourth subsystem or sphere of the Earth system. All right, and this includes all life on Earth. Now, these spheres do not act in isolation. They interact with each other, right? If you just look at a volume of soil, in it, you'll have pore spaces, which have air, they could have water, and they have life, right? So all these systems interact and talk to one another. And when you put them together, they function as the Earth system. So you can't just consider one of these in isolation, especially when dealing with climate and climate modeling. All right, so now let's talk about fluxes. Let's just look at this circle in the center, and let's imagine some storage of material. All right, so that is our volume of material in the center. The white dotted circle is our boundary layer. And a flux is some material or energy moving over time into the system would be input, or out of the system would be output. Now this is just a simple systems flow chart, and we can make these insanely complex, as you will see as we move on with this climate science course. And now, what if we increased the output? What would happen to the system or to the volume stored in the system? Now think about it for a moment. And if output is greater than input, we're going to get a loss in volume. Our storage is going to decline and decline and decline. And it's going to keep declining until there's nothing left. And at that point, when there's nothing left, we have achieved a state of equilibrium, because the volume of stuff inside the system isn't changing. Equilibrium. All right? So now what happens if we reduce output and increase input? We're going to get some material again, right, in the system, and our storage is going to increase and increase and increase again, right? And then if we made input and output equal, we achieve something called steady state. So that's when inputs equal outputs, and the volume stored in the system does not change. And this is also equilibrium, because the volume is not changing. All right, so now let's discuss some different types of systems, and these are entirely based on the sorts of fluxes that we get into and out of the systems. So an open system, we have energy that can come into the system. We have material, all matter that can come into the system. We can have energy that leaves the system, and we can have material that leaves the system. So that is an entirely open system. Free flow of energy and material in and out. So how about a closed system? Well, we also can call this a materially closed system. So this is when we have energy inputs and energy outputs, but we don't have any material coming into and out of the system. All right, so we're only dealing with energy here. So this is a closed system, or it's often called a materially closed system, which I think is a little clearer and easier to comprehend. Lastly, we have an isolated system. And in a perfectly isolated system, you don't have any material or energy inputs or outputs at all. So this is like if you had a supremely awesome insulator. All right, so think of the best cooler you can ever imagine, which lets no energy in at all, or out. Now, Earth is a materially closed system, generally speaking. Yes, we have spaceships that leave sometimes and hopefully usually come back. We have satellites that leave. We have asteroids that come in sometimes. But for the most part, Earth is a materially closed system. We get 99.97% of our energy into the Earth system from the sun, and we lose energy from the Earth system in the form of thermal radiation because Earth has a temperature that's above absolute zero, and you'll learn a little bit more about that when you go through our temperature and thermometer tutorials. And the thing is, any body in the universe that has a temperature above 0 Kelvin, that's absolute zero, emits what is called electromagnetic radiation. And because of the internal kinetic energy, so that's the energy of motion, that's the energy of molecules vibrating around and translating around, right? Vibrating, translating, and rotating. The internal kinetic energy is what gives an object its temperature. And so when you have a temperature of absolute zero, those molecules stop moving. And so no energy is radiated out or emitted. All right, so that is an example of kinetic energy. Now, let's just talk briefly about potential energy. Earth is in a state of hydrostatic equilibrium. This is why our planet does not implode or explode. So as you'll see in the atmosphere video, and which also talks about atmospheric pressure a little later when you go through the content, that because of the different atoms and molecules and compounds that make up the gas that is our air, they move around, right? They exert a force. And they exert this force in multiple directions. And a force over an area is pressure. So the atmosphere exerts a pressure in all directions. And the further down you get in the atmosphere, the greater that pressure becomes. So the closer you are to Earth's surface, the greater the atmospheric pressure is, because the mass of the overlying air is heavier. And so the pressure gradient force pushes everything in all directions. And if we only had a pressure gradient force, the atmosphere would just be pushed away. But we also have another form of potential energy, and that's called gravitational potential energy. So because Earth has a mass and it's a massive body, it is pulling the atmosphere back down towards the surface of Earth through the force of gravity. And so if this force of gravity was greater than the atmosphere's pressure gradient force, the atmosphere would just collapse on top of us, and we would have no atmosphere and we would not be here. And so the atmosphere exists, and it's not crushed and it's not exploded off of us because the pressure gradient force is in balance with the force of gravity. And that is what is called hydrostatic equilibrium. And so remember, when we were talking about equilibrium a few slides ago, that meant that our overall volume of the system wasn't changing, right? They balance. Equilibrium is a balance. All right.